Hey class, thanks for tuning in to Intro to Parent Functions and Transformations. In today's lesson we're going to be looking at what is a parent function, and I'm going to apologize ahead of time for the corny video that's coming up next. But I thought it'd be a good idea for you to see some of the different parents and maybe have a little fun at the same time. So enjoy!
MHS. Yep. Mr. Ground. Oh.
Quadratic, I am a linear. Y equals x to the 1 is my signature. And if you change my B, it moves me up and down. And if you change my M, it moves a slant around. I am the father of lines, so don't you doubt my game. Y equals mx plus b, that is my family's name. Don't know my slope? It's rise over run. I'm at a constant rate. I get done. Don't you know me, y'all? Homie, I'm absolute. I'm so symmetrical. I give the V salute. And if you change my A, it makes me thin or wide. And if you change my H, it slides me to the side. I am the Don of the V's, I don't mess around. Y equals line, X line, written on my crown. If A is positive, you can fill my cup. And if it's negative, I'm vertex up.
Gets higher, they call you Slim Jim. When it's on the low side, you're not looking trim. Y equals x squared, yeah, that's the basics. Ax squared plus bx plus c, let's face it. You graph that parabola, it's up or down. A U to the ceiling and an N to the ground. It gets tedious, but don't start ignoring it. It may go on forever, but the vertex is the origin.
Okay, so that video just gave you a little glimpse at some of the parents we're going to be studying today. And so what we mean by a parent function hopefully was clear. It's the most basic of the functions in a particular related grouping of functions that we would call a family. And so the most basic graph we call the parent graph. So in this introduction, we're going to take a look at what the parent functions look like. And then a separate video, we're going to move on and take a look at what if we take these parent functions and we change them in some way, which is called transforming them, and we'll see what that, how that changes their properties and their locations and things like that. So we're going to start off taking a look at the most basic parent function, which is the linear function. And the parent function for the linear family is y is equal to x, or f of x equals x. And if we were to, say, make a table of values or something like that to graph this, and we just picked x value, like say -3, -2, -1, 0, 1, and 2, no matter what the x coordinates were, the y coordinates would be identical. So we'd have this series of ordered pairs that were duplicates, x and y always the same. And so when we graph that, essentially what that does is splits right through the first and the third quadrants. Remember, this is the first quadrant, and this down here is the third quadrant. And so if we plotted -3, -3, it'd be right here, -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, and so on. And that line just splits right down that first quadrant. And notice that this linear function has a y-intercept of 0 and a slope of 1, and that's about as basic as you can get, and that's really characteristic of a parent graph. Let's answer some questions about this parent. For instance, the domain. So you can see as you work left to right, there is no breaks, so that's all real numbers. And same thing going high to low, that's all real numbers. The x-intercept is at 0, and so is the y-intercept at 0. They cross right at the origin, and so the intercepts are just the same. Now when we say maximum number of roots or zeros, that means solutions. And that means the number of times it could actually cross the x-axis, and the most a line could ever cross the x-axis is 1 time, unless of course it was the x-axis. And so there's one possible root. So linear functions, unless it's a special case where there's none, or when there's infinite, we would say there's 1. And then the end behavior means as we go to the right, so depending on, like with our, and this is with just our parent graph, but as we're looking to the right on the x-axis, you can see how the graph is facing up because it's got a +1 slope. But then on the other side, as I'm going to the left, the graph is facing down. And so in this case, with this parent function, as x is increasing, so is y, and as x is decreasing, so is y. And so one way we describe that is by using infinity. So we would say as x is approaching -infinity, in other words, going to the left, the output f of x is going towards -infinity again. So again, that's basically the same as saying decreasing. Or as x is going towards +infinity, the y is going up also, so it's going towards +infinity as well. And because there's no breaks in this graph, that's not discrete or, set up in pieces where there's a break in it, maybe where there's a spot where there's a particular input you can't put in. This is continuous. So we have a continuous graph. So we've also looked at absolute value graphs. So let's go ahead and look at the parent graph for absolute value. So we know that that is f of x, or y, is equal to the absolute value of x. And we actually just got done graphing absolute value. And so we know that if we made a little table of values, so say we did what we did with the linear graph, and we kind of just created a quick little table where we picked x values and plugged them in. Say plugged in -2, -1, 0, 1, 2. We know that if we put -2 in, we'd get +2 out because absolute value makes it positive. Plug -1 in, we get 1, 0, 1 if we plug 1 in, and 2 if we plug 2 in. And so essentially that makes these points right here, and that vertex is at 0, 0. And we've got the characteristic V shape of an absolute value graph. And so if we wanted to talk about the domain, of course you can take the absolute value of anything, so that's all real numbers. But clearly in the range, the lowest this ever goes is right here at 0. And so for the parent graph, the range is y is greater than or equal to 0. The x and y intercepts are again at the origin at 0 and 0, so for both. So that's where it crosses the x-axis, where it crosses the y-axis. The maximum number of roots for this particular one is 1, but I mean, if you can imagine the sliding the absolute value graph up or down, like say for instance if I slid it down here like this, an absolute value graph could cross the x-axis twice. So if we're being in general, I guess we'd have to say maximum number of possible solutions are 2, and that's why when we would solve absolute value equations, in all cases but 1, we would get 2 solutions. So we're talking about end behavior again. So as we're looking at the ends of the graph, in other words, all the way to the right, so if we're looking all the way to the right over this way, you can see that as the x's are going up, the y's are increasing. And on the other side, the same thing's happening. It's going up in terms of the x's are going down this time, but the outputs are going up because we're taking the absolute value, which makes it positive. And so the way we could describe that end behavior is by using that same way that we did with the linear one, with using infinity. As we're going towards negative infinity, in other words, as we're decreasing the x, going towards the left, the output is increasing, so it's going towards positive infinity because it's pointing up. And then as we're going towards positive infinity for the x, in other words, positive x values and increasing, then that means the graph is also increasing because it's, again, pointing up. Like this right here on that side, it's pointing up as we're going to the right. That's what that's saying. Now this graph is a continuous graph. There is no breaks in the graph in terms of left to right. There's no no value you can't put in for x, so it's continuous. Now in the silly video you saw the quadratic graphs, and the most basic quadratic function, or the parent function, is f of x is equal to x squared. And so again, we could create a table if we wanted to graph this, and you think about what we're doing to it. Whatever we're plugging in, we're squaring it, which is kind of like with absolute value. It's always going to make it positive unless it's 0, which makes it 0. So say I put negative 2 in and I squared that, I'd get 4. Put a negative 1 in, square it, I'd get 1. Plug a 0 in, 0. If I plug 1 in, that's 1. Plug 2 in, square it, that's 4. And if I plotted those out, at negative 2, I'd be up here at 4. At negative 1, I'd be at 1. At 0, I'd be at 0. 1, 1, 2, 4. And remember from Algebra 1, this is that little smiley face looking graph. Kind of, well, someone would be really happy if that was their smile. But that's called a parabola. Let's go through the same thing. So with quadratic, the domain is all real numbers. I can put anything in because I'm squaring it. But just think about, and you can tell by the graph too, that the lowest this thing ever gets is right down here at 0. It never gets further than that for the parent graph. So we know that the range is greater than or equal to 0 because when we square things, the lowest we can ever get is 0. Otherwise, it's positive. The x and y intercepts are again at 0. So you see this pattern happening, that these descriptions are really similar. Not identical, but very similar. So the maximum number of roots, again, if you can kind of imagine sliding this up or down, there's 2 possible roots or zeros. It's 2 places the graph could cross. Like, say, for instance, if I had a parabola like this, see how it crosses the x-axis 2 times, which are called the roots. And so we know that that's possible to have 2. We'll talk about how it can also have 1 or none. But then the end behavior is just like with the absolute value. So if we just duplicated what we had for absolute value, because as we're going to the left, in other words, smaller and smaller x values, you can see that the graph, this end right here, is facing up, because see how it's going up like that as we're going this way. And so that's, again, as we're going towards negative infinity for the x, the y's or the outputs are going up. And so a way of saying going up is saying positive infinity. As we're going towards positive infinity, in other words, to the right, the graph's also facing up. I'm not very good with the infinity sign, sorry. So it's going towards positive infinity as well. And this is a continuous function. So you see, the only thing that really is changing here so far is this end behavior, and that's because with a parabola and absolute value, the ends go in the same directions, or they agree. Whereas with a line, one end went up and the other end went down. So let's go ahead and turn the page and look at some more parents. So now there are many other parent functions. There's other families of functions we're going to study. But our main focus is going to be on linear, absolute value, and quadratic for the near future. So we're going to actually end with this parent function, the quadratic parent function. The reason why I gave you all of the parents on the same sheet is because we'll keep coming back to this, and as we explore new families of functions and study them and their characteristics, we'll take a look at the start at their parent function. So we're going to hold on to this sheet and we'll come back to it at a later time. So that actually it does it for our lesson today.